Hello and welcome to Basler University. In this video we're going to provide an introduction to the BE1-FLEX protective relay and show not only can it do protective functions but so many other things in a power system. One of the first things we're going to show is the application flexibility. The Flex is extremely unique in this environment in terms of how it goes about protecting equipment, both from a single breaker and single point as well as multiple points. And we could do this not only with one piece of firmware, but literally the exact same box can be applied to pretty much anywhere in your protective relay system, or even control system if you wish to use it for the control functions. We have some highlights to show a little bit of how we do that, and we're going to walk through a couple application examples, both on paper as well as walk through a little bit of a brief tutorial with our Best Comms Plus software to show how to do these things. So first we're going to go into application flexibility. Again, a lot of traditional protective relays have very dedicated purpose and dedicated functions. The BE1-FLEX is extremely different. It can apply itself to pretty much any application, and we'll get into a little bit how and why it does that. But again, keep in mind, this isn't being able to tweak it for different applications. You can literally apply it to anything and just turn on whatever functionality you want. It's one of the fundamental differences between the Flex and most anything else you're going to see out there. From a protective relay standpoint, one of the core points that protective relays exist is in feeder protection. So feeder protection historically has often existed with overcurrent protection. Those are 50 and 51 elements. If you wish to have directionality or negative sequence or other variation algorithms on that, you would call them 46 functions, 67s, or a variety of other things. Additionally, in lots of places you're going to have things like voltage protection, such as over or under voltage, over or under frequency, or even rate of change frequency. Common in utility systems is a reclosing function on those feeder protections. With the Flex, you style it appropriately and you can turn on any of these functions. We'll show the style chart in a little bit of how we do that, but again, just keep in mind you can strip it all the way down into basic feeder protection if you wish, or you can build it as complex as you wish into multi-breaker or any type of functionality you wish to build into it. Another common application is a transformer protection. So very similar to a feeder protection, has a lot of the same functions, but one of the cores to most and many transformer applications is a differential function. The differential function is looking at current in and current out and making sure they balance. With transformers, you need to make sure that you can measure all of the currents that do go in and out of that transformer. So for a two-winding transformer, that would generically be phase A, B, and C on both sides of the transformer, so 6 current inputs, but there might be 2, 3, or 4 winding transformers, even tertiary connections that might result in 12 or more current inputs needing to go into the protective relay. With the BE1-FLEX, you just build it however you wish to bring in and have all that hardware input capability built into it. If you wish to do temperature monitoring via RTDs, for example, you can bring that in as well. And there's additionally some additional functions such as through fault counters and more predictive type functionality that is built in and available to you if you wish to utilize it. Again, 50-51s, overcurrents, directionality, that's all available as well, of course. In this diagram, we see the first example of a 2-breaker configuration. Sometimes a transformer has a breaker on one side, sometimes on the other, sometimes both. Doesn't really matter. With the Flex, you just bring in what's necessary and you tell the configuration what it's looking at. Generator protection, again, this varies quite a bit across applications and purposes. It depends upon what you're trying to do with it. And same thing I'm going to say probably about 15 times today is just build the Flex into whatever you want it to be. It doesn't have a set list of functions, and you're not going to hit limitations for how much you can put into it. So for generator protection, some of the more advanced functions, in addition to the common ones that we've seen before, you might be using a distance function, whether that's phase or neutral. Differential protection, again with the 87, is very common on a generator protection application. From an algorithm standpoint, it's the same algorithm in the BE1-FLEX that we can apply to either a generator or a transformer, or even both if you happen to have a unit differential, but you can apply it to both or either as you wish. Some of the other functions, it can do automatic synchronizing, can do reverse power on even a single phase, so you can have a single phase reverse power condition. Loss of excitation can be either VAR based or impedance based. And a couple of the other ones that are semi-unique to generator-based applications are out of step what was the other one I was looking for? The 40Z or the 40Q I'd already mentioned. We can additionally do 100% state or ground by using a 59N and an undervoltage third harmonic view. So lots of different ways you can build up whatever application protection is required and necessary for that particular piece of hardware. As we start to look at kind of the larger range of what somebody might be able to do with a protective relay, a low impedance, low Z means low impedance, bus protection happens to be one of the more hardware intensive applications that protective relays do. And they do that because they need to monitor all of the current inputs on all of the lines that are going into and out of the bus. So if you're doing a three-phase bus differential, that'd be phase A, B, and C for every single breaker, assuming you're talking about a three-phase system. So in this particular example, it would be the main breaker and 5 feeders, so 6 times 3 is going to be 18 current inputs would have to come into the protective relay in order to do this as a low impedance bus differential. The Flex can certainly do that. We can also monitor bus protection or bus voltage. With that, we can get power and all sorts of things across all of the feeders. One of the heavy differences and benefits of low impedance instead of high impedance bus protection is because a low impedance protective relay brings all of the current transformer signals directly into the box. And because it does that, it can actually see the currents at each point. A high impedance bus protection application is going to have those current transformers wired together external to the relay, and therefore the relay is only seeing the total and the accumulation of all of those. The downside to that is you can't see individual feeders or individual current transformers, and therefore can't do overcurrent protection and things additional to differential. So there are applications where high impedance bus protection is beneficial. Speed happens to be one of those specific points. But in many applications, the speed variance between low impedance and high impedance isn't significant enough to outweigh the benefit of going to low impedance. With the Flex, we can do up to 28 current inputs into a single box. And with that, we can do theoretically up to 28 single phase circuits protected by a single protective relay. We would do that with single phase and potentially even use multiple devices for a three-phase system. Microgrids, again, this is just a simple example of what one might look like from a very generic perspective, but the whole idea is you have a variety of sources, you have a variety of loads. Current is not necessarily going linearly from the utility generator all the way down to the load. It could be a wide variety of things. And with the Flex, we don't know what these applications are going to be, in the future, so we designed the Flex to be able to handle anything and be able to just tweak and modify over time, either by ourselves or by field and users, to whatever functions might be desired. One of the more specific ones that's common in what a lot of generic microgrids are is what you see in the top middle. It's a solar panel, and those are DC power. So you've got the inverter coming in. The Flex has the ability to bring in shunt inputs instead of current transformers, and with that we can actually see direct current over current. Something that's not very common in many protective relays, and we can do it in addition to all the other things that we're doing. Another thing that's very important about a microgrid type application is going to be automatic synchronization. So when you have multiple sources available, in this particular example we have a utility power source up at the top left, let's say a backup generator bottom left, a solar panel, and maybe even a battery system bottom middle. Any of those could potentially power and synchronize that load, and therefore you have to be able to mix and match and be able to synchronize to a wide variety of different system configurations in order to manage that system. The BE1-FLEX could do this with multiple boxes or even a single box, depending upon user preference on consolidating versus distributing that decision making, or even a hybrid of both. Another thing that is important to remember about microgrid systems is when systems are non-radial, so when they do not have just, again, a single direct path from generation source to load, the overcurrents can have difficulties in seeing different fault conditions because those currents might cancel each other out. So things like distance protection and bus protection and directionality become more and more important because standard overcurrent just can't see it electrically. Now we're going to walk into a couple of the key highlights. So how do we do all of these things is what we'll start discussing. Right off the bat, we'll look at the hardware. How do we get information into and out of the box? We have 7 available slots. The top is always going to be power supply, because you always have to turn the lights on in the processor. And then for the most part, slots 2 through 7 are extremely adaptable into any mix and match of what a user might want the application to do. So we're not trying to do every application under the sun at the same time. We're trying to let a user build a box and build a system exactly for what its intention is, with also the ability to modify it down the road. These boards, as you can see, have screws on the left and right of them, and those are intentionally for users to be able to swap and mix and match and make changes in the field. Product longevity is one of the goals of the Flex, is making sure that it's relevant not only today, but relevant 5, 10, 15, 20 years from now as system needs change. It also goes towards cybersecurity and other things inside the box that we'll just barely touch on in today. We'll have other sessions on in the future. So again, 7 slots, mix and match them however you want, and even make changes in the field very easily if you wish. So how do we do this? With typical configuration stuff, you might have pages and pages and pages of different choices. We're able to allow you to configure the Flex into any of 500,000 plus different variations. We can do it just with this simple of a layout. And the way we do it is because we allow you to just simply select what boards you need to provide for a specific application. So in this particular example, I have 2 of the T3 boards, which brings in 8 channels of voltage. That's 4 times 2. And the same is 4 times 2 is 8 channels of current. On the communication board, we're using the E5, which provides a copper Ethernet port plus some contact I/O, and you have other boards available if you wish. On the contact input and output boards, these are basically our I/O boards. Again, select whichever combination you wish. And this particular example has 10 contact inputs, and 2 plus 2 is 4 times 2, 8 contact outputs. So this total accumulated input-output combination is going to have 5 plus 3, so 8 inputs. And then I have 8 plus 3 more, 11 outputs. So again, mix and match it however you wish to build in whatever combination of stuff coming into and out of the box as you need. Again, if you happen to style it wrong, just know that you can always make changes in the field to literally any Flex style. And you don't even need to do that with a hardware change necessarily. Just mix and match and you can be off and running and on the fly. Down in the bottom right, I have my button choices. So power supply, it always requires one because you always have to turn it on. So just make your selection. Terminal kit is for the non-analog boards. The analog boards are always ring tongue lug, but all the contact I/O, for example, is going to be connectorized, and those you can select as spring or screw type. And the protection and protocol packages is really what sets the Flex aside. The protection is hierarchical. So if I select enhanced, I can have any protective function in the box, and I can have any number of those functions. For cost purposes, if you wish to scale it back, you can. And if you wish to change this in the field, you can purchase a style upgrade kit from us, which is just a firmware file, and we'll send it out, and you can upload your unit without even having to remove it from the panel. Same theory for protocols. So as cyber and as communication languages and things evolve over time, we can update this to any functionality you wish to have for it. This is the protection packages in a little bit greater detail. So if you had remember the previous screen, you had seen none, and that's, let's say if somebody would like to use it for just a control application or a meter device or a fault recorder, anything along those lines, you could just strip down the cost and not provide any true protective functions. If I look at the basic current, which is the yellow square, those are the protective functions that are included in their basic current package. Same theory for voltage, and I'm going to go skip all the way up to enhanced, and the enhanced can do any of those functions and any number of those functions. So when I come into multi-breaker applications, I don't really care if it's a generator or a transformer or a load or whatever it is in making that total combination of functions, because the Flex can just turn on whatever functions you wish to have. In addition to that, we have configurable elements and math elements. Those are for things that we don't yet know about. So as our markets and needs evolve, the Flex has the ability to do math and lets users design things basically on the fly. One of the places that might come into play is total harmonic distortion, THD, for example. So as we have more inverter-based resources such as solar panels and such, harmonics and other things of the system change because those are DC sources. Anytime there's a DC source, there is a possibility of harmonics and different fluctuations that are not standard and traditional for heavy rotating equipment AC systems. So with our configurable protection, you can just turn on a protective relay to look at total harmonic distortion and protect and trip at real-time speeds on harmonics. Again, I had mentioned the none a metering transducer. Think about all sorts of other things that you could do or wish to do with a device that's very reliable and fast and cost-effective, such as a protective relay. From the human interface perspective, we took the angle of no news is good news. So as things get more complex, there's always this checks and balance that needs to happen to make sure that they're not so complex that they can't be used. So human interface and human interaction is a big part of what we designed the Flex to do. So how do you do all these things with having it not become overwhelming and overbearing? One of the things that we've really done is simplified the layout, simplified the human interaction in terms of how you navigate through the screens, and given the user the ability to do custom screens so they can show exactly what they want. So instead of having all these dedicated devices that have buttons and things in specific places, you could show that on the screen. And we'll get into a little bit of that as we go through future slides. Again, sensory overload. It takes true learning and operations knowledge to know what all those greens and reds and switches do. The more we can put into a protective relay in the settings from the design side of things, it can straightforwardly tell a user what it's doing, what the function is. It can be in user terms or user language as opposed to cryptic languages that protective relays have often used historically, and make it much more intuitive to use. The screen will go to sleep, and that's very much intentional because, again, if everything's running and up and fine, the screen will go to sleep and all you have to do is tap it to wake it back up. And there will always be indicators on the bottom to tell you that everything's okay. So if the green power light is on, that means it's powered on, happy and healthy, and all the other lights will be red if they do enunciate, and that's to tell you, hey, something has occurred at this point, so maybe wake the screen up and take a look if you're interested. So the home screen is really where we show a huge portion of what's happening in the system. So if you remember the previous slide, I had a whole bunch of dials and switches and all sorts of things that were custom to that piece of switchgear. We can replicate and do a huge portion of that from the home screen of a Flex. The top half of it is what we call our system one-line space. This is 100% configurable. It's drawn in SVG format, which is open protocol. So you can literally drop in pretty much any graphics and images you want. It can do animation, it can do color changes, it can do whatever you wish. We have a lot of templates that are available. We can support you in helping create other graphics as you wish, or you're fully welcome to do 100% of your own graphics and designs. So, and again, any mix and match of what you want that screen to show, we can show it up there from that perspective. On the bottom right, we have indicators. As you can see, a couple different colors here. Names can be user configurable. That again tells the user specifically what's happening as opposed to some cryptic knowledge of it. And then on the bottom left is our switches. Switches and buttons and control actions such as break or operate or maintenance mode switch and things like that. Control with confidence. So because there's control, and one of the things that we've heard is if it's a touch screen, there's some concern over making sure I don't accidentally touch it. So there's a couple different layers of protections against this. You can put the control behind security. So because it's behind security, you have the ability to lock it down and make sure that nobody accidentally does control that's not trying to do so, or even intentionally does control that they shouldn't be doing. In addition to that, let's say a user is appropriate to do control functions. Somebody might be concerned that if they tap accidentally twice, it might perform an operation accidentally. So we have 2-point operation. So every time you press a button, the second button, so the operate, select will be in one location of your physical touch, and the second button, which would be the operate, is going to be in a different spot. So no matter where that button is, it's going to move that operate to a different piece. Doesn't seem like a big thing, but if anybody's accidentally double-clicked something, you'll know, sometimes it does cause some issue for that to occur. And again, we can always require login if users do, and that's just in the standard settings files. The enunciator is on the lower right quarter of the protective relay and on the home screen, and you can have up to 255 points in our indicators. On the home screen, depending upon the length of the name, we can show up to about 12 or 14 of them. 7 or 8 is typical if you're using potentially 2 lines each, but you can do more if you wish, and you can color code them, and you can enunciate any logical point in the relay. These enunciators / indicators are programmed in logic, and you just drop them wherever you wish to in logic. So in this particular example, I've got some single phase under voltage targets that somebody had wanted to enunciate, but literally any logic state if you want. Potentially you would want to know if your bus is healthy or anything like that, just tied to whatever logic chunk you wish, and then you have an enunciator. Again, because they're color coded, you can manage it because green and red don't always suffice. Green might not be good, but red might not be bad, and vice versa. So enunciate them as you wish. And by the way, because there's 255, if you wish to use more than the 8 to 12, 14 that can be on the home screen, you can map any of the bottom hyperlinks of the home screen to the enunciator page, and it'll show a full list of all of them. You can also navigate through the menu button in the bottom right of the home screen and see those enunciators as well. So how do we, again, kind of do these things from a simple standpoint? One of the things that we do is as you're creating logic, it's always graphical and always visual. We do that because it's far too easy to misalign, to turn an AND gate into a NAND gate, and things like that that just make it very easy to create errors if you're not looking at it with a picture. The picture is much more intuitive. You see a lot more information at one time. In addition to that, we have the ability to do logic simulation. So as you're creating the logic, you can click the Turn On Simulation button, and it'll show you what the status is. Because it's an offline simulation, if I want to manually operate, let's say an 81 over frequency, I would just double click the word trip and have it run through and see what happens in my logic. So that's the offline simulation that somebody would do for perhaps when they're creating a settings file, if they're trying to debug a settings file to make sure it's what they want it to be. In addition to that, in the metering screen of our BestComms Plus, we have what we call live logic metering. And live logic metering is actually looking inside of a live device and showing you all of the true-false states within the logic. The graphics are 100% identical to the settings. So when somebody creates the settings, they have additionally automatically created this live logic view, and I'll just press play to give a quick example of what this live logic does. In this example, I've got an overcurrent 50-1 and a switch 43-1 that are tied to an OR gate and an output. So I'm going to manually operate that 43 and watch it go through the OR gate, and therefore watch the output operate. So if and when this is in front of a physical relay, you would actually hear that physical output operate because that's what's happening in this particular chunk of logic. So again, this is live status. This is exactly what's going on inside the box, and very helpful if you have complex logic, or if you have if you're stuck in commissioning, or if you have a troubleshooting situation where something's not doing what you want it to do. Let's say if you have counters or feedback loops or all sorts of other fun, non-direct things could be seen in direct status by using that live logic metering. So because it's a 7-inch touchscreen, we can show a huge portion of information, but even I wear reading glasses sometimes, so sometimes it's very helpful to have a pinch to zoom. So just as you can pinch to zoom on lots of applications, let's say on an iPad or other touchscreen type device, you can pinch to zoom on the Flex and zoom in. We can show, again, that same logical graphics on the screen of the Flex to show an operator what's happening. And by the way, you also see this notes field, this light yellow box right there. That's so when a person creates the settings, they can actually put notes on that logic to show an operator exactly what's happening. So not only can I show the graphics of what's going on, I can put notes on there, and I can even pinch to zoom so they can get incredibly detailed information just from the HMI of the Flex. Another function that the Flex has natively is going to be advanced recording. So it's got a very strong and huge processor in it for a protective relay, as a 30 million point data array, and you can trigger it with a huge portion of functions. So by default, the protective functions are going to have the fault recorder turned on. You can turn it off, for example, if you are just having a control function or something that you don't want to use up your oscillography capture information for that. Down in the lower right, you see an example of the fault recorder being able to be turned on if you wish. If you want to trigger it with something, let's say a contact input with a goose message or anything like that, you can drive that in logic accordingly. And again, 30 million data point array, and it samples at 128 samples per cycle, which gives you the ability to see harmonics up to the 63rd order. So it's getting very granular in terms of how fast and what it can capture. In addition to the fault capture, so that's the oscillography, in addition to that, we can do sequence of events, and that log is automatically default again by is enabled by default automatically. 8,000 events. It's going to record the first in, first out sequence of any digital transition in the device. So if an element picks up, if somebody logs in, any sort of condition like that is going to record it in the sequence of events. If there's events that you don't want to record, you can uncheck a good number of them in the settings if you wish. Most people just leave them all on, and that way they scan through and find what they need if there ever is an operation or necessity to look at the events log. So with a lot of this, we have made sure to enable as much as we possibly can safely, and that way users don't accidentally forget to turn it on. So one of the things that's very helpful with digital protective relays is the ability to record information, but if it's not recording, if it's not turned on, then it kind of defeats the purpose. So we do a lot of these default enabled type things in the Flex, but also keeping in mind that we will never turn on a protective function because we're never going to put a set point in there because we don't want it arbitrarily tripping, as opposed to arbitrarily recording information that's not used as harmless. It's just sitting in the relay and just logging information that may or may not be useful, may or may not be necessary, but it's there if and when it becomes necessary. Another graphics that we have is the synchronization. So with any breaker instance that somebody creates, we have a synchrophaser scope, a synchronization scope that is available on the HMI. The synchronization scope shows both the voltage and the frequency deviation and when it's in sync. So a really helpful one-spot tool to give yourself an angle and magnitude synchronization viewpoint. So anybody that's ever looked at a synchroscope over the years, this will look familiar to them. And anytime there's a breaker instance that has voltage on both sides of it, and the synchroscope is going to populate. A bunch of the communication options that are available in the BE1-FLEX are shown here. I'm not necessarily going to read them all off, but a couple of key ones that are more up and coming and common questions are going to be things such as synchrophasers, IEC 62850, PRP and HSR have to do with redundant Ethernet ports, so we can do all of those. And again, depending upon how you configure or style the Flex, any or all of these can be available to you. One of the things with our Ethernet ports is they can support multiple languages at a time. So if you have, let's say, a legacy DNP3 system and you want to use some of the functionality of IEC 62850, you could do those in parallel, and you can even migrate over time. Again, kind of take the reins off of what you wish to do with it. The Flex just makes it very easy to apply what you wish to and also give you the option to do other things down the road. A couple of the hands-on tools, and we'll kind of skip to them here in a brief moment, but the idea is for the Flex to be as user intuitive as possible, also as easy to apply and deploy as possible. So we provide two-dimensional and three-dimensional graphics for your mechanicals. We have a lot of application and guide form specs that are available on the website. I have a lot of videos, this video being one of them, kind of walk you through things that it can do. There'll be more of them, as we kind of continue to build up Basel University material, and I'll just do a click on the BE1-FLEX page on Basler.com. So here's the main page of the BE1-FLEX on Basler.com, and if I kind of scroll down, one of the main things I wanted to show you is the Flex configurator. So I had shown you that to select the number of boards, let's say I want 2 of the T3 boards. In my other example, I'd already given 2 of the W9s, I'd populated an E5. I don't specifically remember which of these selections, so I'll just make some button choices, enhanced, and protocol 02. Once I get rid of all my red things, I know that I've created a valid style number. It'll pop up here. I can copy it, paste it out. I can even generate a guide form specification that is exact to that configuration. So you're not going to have guide forms that say, hey, I can do up to 28 CT inputs. It's going to say specifically this style has 2 times 4. It has 8 current inputs, and that's going to be in that guide form specification. You can just download with one click. Additionally, I can update my 3D view. So with the update of 3D view, it can give me a physical representation of exactly what that looks like. So again, it takes a lot of that guesswork out of not knowing what that device is going to do. Let's say I wanted to add another board. Let's see. Let's add one over here instead. Let's say I want to take away a board. If I wanted to take away a board, let's say I don't need that T3. Once I update 3D view, I'm going to see this slot go back to a blank slot. And now when I go back, now it's a blank slot, and I'm off and running. So that's one of the tools that's on our Basler.com page, specific to the Flex. And there's a bunch of other things that you can get into as we get into more detail later. And that's the hands-on tools that you see available. We're going to walk in a little more detail of a couple application examples and kind of show how we do these things and where we might doing it. So this particular example is going to be, let's say, a unit differential or a unit sub that is going to include a generator as well as a step-up transformer. In this particular example, it has 2 breakers in this scheme, and the current transformer locations and voltage transformer locations are really a couple of key pieces that are necessary to know what can it protect and how much information do I need to bring in and out of the box. With the ability to do up to 10 differential zones in a protective relay, I can have one zone based upon the location of those current transformers protecting and having very tight settings specific to generator protection. I can do the same thing for my transformer zone with current transformers on both sides of that current the power transformer. So that's my transformer zone. Additionally, I can have a supervising unit differential that's looking around the whole thing, and that way I'm additionally protecting this breaker and also giving the ability to have tight set differentials around the individual resource. Mix and match these functions however you wish. Again, current and voltage sensing locations are one of the key pieces that allow this to do a whole bunch of these things. If you want to do synchronization, sync check, 11 is the multifunction device. So again, whatever you want to put into it, you can put into protective relay, a single box protective relay. If you wanted to break this up into different zones, different boxes, of course you can do that. You can strip it down into only what you want for a specific application. And also redundancy comes into play in many applications where one method might be to have 2 of the same box, one might be to have different boxes. Whichever methodology fits the needs of the application the best, Flex can build itself into that specific thing. Another example is, let's say, a main-time-main application. In the main-time-main application, this tiebreaker is going to be typically open, and these 2 sources are going to be feeding these 2 loads under normal states. With a main-time-main, you have a tiebreaker, so if either of those sources is unhealthy, this tiebreaker will close, the other breaker will open, and therefore both loads will be fed by only one source. So there's a number of different methods that you can do to provide main-time-main protection. You can do it with one box of the Flex. You could also do it with 2 or 3 boxes if you wish to have dedicated devices on each segment. So again, determine what is most beneficial for application needs and build the Flex accordingly to that. In addition to just the breaker control, we can also do full protection, such as intertie protection with this exact piece of hardware. We can also do cumulative load. So maybe the plant or the facility down here wants to know how much power am I receiving from this source plus this source for whatever reason. The Flex has what's called virtual circuits that can accumulate and sum those 2 things and look at it as if it's a real measurement from a single current transformer and voltage transformer. So again, lots of different ways you can mix and match, again giving so much performance and capability to the designer and the operators to do what they want as opposed to being fixed into a box that's set for a specific application. And here's the main-time-main in a little bit more detail. In these applications, we're looking at voltage oftentimes on the 2 sources, as well as both sides of that tie breaker on the bus, and that allows sync check to occur across this breaker, sync check to across this breaker, as well as this breaker. Anytime you're doing a control of closing breakers, you almost always want to do a sync check function to make sure that those voltages and angles are within tolerance, and that's assuming that you have other load sources or any other non-zero power condition down towards the load side. In addition to that, again, I mentioned the intertie stuff. We can do all those intertie functions at those points if you wish, in addition to all the other stuff. One of the things that I do mention quite often is you're not going to slow the flex down. You can't put in so many functions that the processing is going to slow down. There's even a capacity meter in the settings file or in the settings explorer that will show you that you are within the bounds, and the flex will not allow you to send up a settings file that is going to slow it down and make it do more than it can do. So there's protections there to make sure inadvertent errors don't occur. And again, here's how we configure it. In this particular example, let's say I need to bring in 3 plus 3 currents, so I need to bring in 6 currents. I need to bring in 3 plus 3 plus 1 plus 1, so I need to bring in 8 voltages. Let's just say a bunch of I/O, let's say 7 of each or something like that. So to do that, I would bring in, I need again 8 currents, so I bring in 4 times 2, there's my 8 voltages, and for my currents I needed to bring in 6, so 4 times 2 gives me more than 6, so I'm good there. On the input-output side, I had used this example previously, so I have 5 times 2 is 10, plus another 3 on the communication board, so that's 13, that's enough for me, and 4 times 2 is 8, plus another 3, 11 outputs, again, enough for me. From a protection standpoint, if I look at that previous drawing, the intermediate package gives me everything I need. I don't need, let's say, automatic synchronization or distance or direct differential that's added in the enhanced, so I can drop my cost down a little bit. And for communication, let's say I'm just using Modbus or DNP, and that would be available in package 1. So that's how you would configure a flex for that specific application. If I want to do more with it, again, I've got an extra slot here. I can change my protection and protocol packages. I can mix and match these things to build how I wish it to be. So next, I'm just going to do a real quick run through of BestComms Plus to show how we do some of these things. So BestComms Plus is a no-cost software. It is Basler Electric's software for a wide variety of our digital products. I'm going to open up a BE1-FLEX settings file, and this is just a brand new file, so it doesn't have anything set up to it, and you can kind of see how it's going to outlook. In the Metering Explorer, that's going to be my real-time data. I'm not using that, so I'll make my Settings Explorer larger. First thing I'm going to do is under Style Configuration, I'm going to populate that same style I had used before. Enhance Protection, and now once I auto-generate instance, I'm going to create a bunch of arrows over here. Because the Flex can go into any application, we also don't know what somebody might want to use it for. So there's no breakers, no circuits, because again, we don't even know what hardware is going to be mapped to it. To make it easier on the settings, we have this auto generate instance button, and when somebody presses it, it will create all of that for you. So if you don't want it to create any piece of that auto populate, you can turn it off. If you want to modify it, you can do so. But a lot of times the auto-populate is going to get you very far, if not all the way to your configuration. Another way to think of this configuration is going to be the analog to digital conversion. So we're bringing in analog devices. We're ultimately processing them with a microprocessor that's a digital component. So this analog to digital, let's say for the circuit piece, it had taken slot 7 hardware, looking at voltage ABC, and applied it to circuit 1's voltage phase. Similarly, it's looking at slot 7 currents and mapping that to current. And maybe I'm going to call this my generator circuit. And that's just, now when I go up to my circuit summary, I can see that generator circuit was created and I have that hardware that's mapped to it. It also had created circuit 2, and maybe this is going to be my differential currents. I'm kind of just making up an example as I go here, so nothing in particular about this being correct or wrong, just showing how it's configured. In this particular case, I'm looking at slot 6 currents and mapping them to the differential current circuit. Now every time I want to use that hardware down the road, in the settings I would just look for differential current, which is what I named circuit 2, or generator, which is what I named circuit 1. Similar functions for breakers, inputs and outputs. I can name these, I can map them however I want from the hardware into things that the settings file and the relay is going to use on the digital side. On the protection, that's what you're going to do with protective relay most of the time. If I want to turn on any function I want, I can just go through this drop-down list, and let's say I want to add an instantaneous overcurrent. If I wanted to name it, let's say generator, I can name it however I want, and that way, again, that is a username that is not cryptic or something that user necessarily needs to remember about the Flex. In addition to that, I see this huge function instance counts of up to 255. That means that if I wanted to add up to 255, I just keep clicking add until I have all the functions that are necessary for that application. I'm only going to do one just in the sake of time and interest, and same thing with a time overcurrent. Same process, rinse, repeat for whatever functions you want to apply to it. And then once I have either the functions set up, or I could do it bouncing back and forth if I wish, I'm going to turn and click that gray button in order to turn it on. So I need to give it a mode. These are different algorithms. So an I2, for example, looking at current, is going to be a 46 function, or sometimes also called a 50Q. A 3-phase is a standard 50-phase element. I give it a source. So remember, if up in the circuits, I had named it generator or differential currents. I want to use and look at my generator source, so that's the current inputs, and then what pickup level do I want it to pick up at, and if I want an intentional time delay, do I want to add an intentional time delay? And I'm going to say 0, and in this particular case, that's going to make the 50 element pickup go true at the same time as the 50 element trip. So next I'm going to go down to my click protection again to get back to my summary, click 50-1. Same thing, check my source, give it a pickup level, give it a time curve. You can select any time curve you want. It even gives you a nice graphic on the side. Give it a time dial, things that you're going to have calculated with coordination settings in this particular example. One of the things I do mention is if you hover over the graph, it does actually show you the calculated values. So especially from a troubleshooting perspective or even just a sanity check, it's a nice little way to see, is this the curve that I wanted to operate on? A bunch of other functions, a bunch of other things. There's even show advanced on a bunch of the setting screens that are kind of the non-typical or non-everyday user. And the reason that we do that is so somebody knows that they likely have everything seen that they want to, and if they wanted to get into more complex algorithms, they would click the advanced and utilize that function there. So now I have protection, I have 2 green dots, and I can actually trip something. I go down into my best logic, and now I'm going to actually drive outputs. So I go to my Elements tab, I grab those 2 elements that I had created, I drag them over. I go to my Components tab, I grab an OR gate, because I don't care which one trips. If either one goes to trip, I want to trip that breaker in this particular example. And then I go to my Outputs tab, and I'm just going to use output 1 just for simplicity. And now I've got a happy and healthy logic file. Down on the bottom right, I have even an indication that it's going to be a happy and healthy file in terms of the relay accepting it. Doesn't mean that it's a logical thing for a protective relay to do for that specific application, but this is going to tell you if you have programming errors, for example, in terms of broken lines. So let's say if I accidentally broke that line and I have this red dot here, then my compile check turns to red because I accidentally clicked something wrong. So once I save it, all those turn to green and I'm happy and good to go. In addition to the logic, what's also happened is I've turned on targets, I've turned on sequence events, had a handful of alarms turned on, the fault recorder is turned on, and again, a bunch of those things behind the scenes that it's done automatically. If I did want to do the simulator I had shown previously, I can turn on just by clicking my offline simulator, double click a trip, watch it flow through the logic, and in this particular case, very simple logic, but I'll watch output 1 transition. So turn that off, and this is a happy and healthy settings file that I can upload to a relay. Most applications are going to use additional functions or additional things, so just take that same methodology, turn on the pieces of the settings file that you wish to utilize, and then when you're all said and done, save that settings file. When you're physically in front of the relay, you would would upload and download the settings from the device, and then you're off and running. That is the end and the conclusion of today's presentation, so I thank you very much for your time.